Okay, so good afternoon, everyone. Today, the Atom Seminar has the great pleasure of welcoming Professor Jodie Lutkenhaus. Dr. Lutkenhaus received her diploma in chemical engineering at the University of Texas at Austin. Then, she received her PhD from the Massachusetts Institute of Technology. And nowadays, she is a professor of chemical engineering at Texas A&M University. Dr. Lutkenhaus' research and teaching interests are in the fields of development of new materials for energy storage and smart coatings, including polyelectrolytes and redox-active polymers. Among her several contributions, she received the Young Scientist Award from the World Economic Forum for her works in sustainable batteries using organic polymers as alternative energy resources. So once again, welcome Professor Jodie Lutkenhaus. And thank you so much for being here, and please feel free to start your presentation.
Thank you so much for the introduction. I am really looking forward to this presentation and interacting with you all. I was in Brazil last year for the Equiphase conference, so I recognize some of the names on the Zoom, so it's really nice to see you and connect with you again. So at Equiphase, I talked about our work on the bubble point and confinement, and I didn't want to give the same presentation because we need to entertain. So we're going to talk about our work on polyelectrolyte complexes. And this relates, as you'll see, to some thermodynamic concepts such as glass transition, how the polymers relax, and then the energy of that relaxation. And you'll see how salt and water really play a role in how these polymers come together and the dynamics of these polymers. So my group does a lot of the experimental work. We also collaborate very heavily with Maria Samuel-Corpy and Peter Bottas. They do molecular dynamics simulations to give us insight into the physical phenomena that we're observing. And I won't show too much of the MD simulations, but I want to mention them so that you can also follow their work. Now, I am at Texas A&M University. I wanted to share a little bit about my institution because we are so far away and maybe you haven't visited us in the past. We are a university that was founded in 1876. We're a very large university. We cover over 5,200 acres of land. We have 73,000 students, 21,000 of those are engineering students. So our university is famous for its engineering education. We have over $1 billion in research expenditures. And then out of public institutions, we're ranked 8th in the United States. So one of the popular sayings at Texas A&M University is howdy. So instead of saying hello, you say howdy. Just like you might see in an old Western movie, that people really do say that. I say that. This is a picture of the building we work in. It's all chemical engineering. This is a picture of our school mascot, Reveille, just a beautiful dog, and students take Reveille around campus. If Reveille barks, class is dismissed. So that's one of these traditions. And here's a picture of one of the older buildings on campus. And then to give you an idea of location, this map shows you that our university is closest to Houston. We're about an hour and a half from Houston, 2 hours from Austin, and 3 hours from Dallas. So we're one of the larger small towns in that area. So I wouldn't call us a city, but we are more of a town. Now on to the science. Now we are going to learn about polyelectrolyte complexes, and these are formed when oppositely charged polymers associate in solution. So it almost always, I don't think this video is going to play because I have the laser pointer going on. Let me get that out. Let me turn that off. There we go. So if you take a solution of two solutions of oppositely charged polymers, when you mix them, the polymers associate into a larger structure that we call a complex. And that structure can be liquid or solid-like, but it's large enough to scatter light. And there's many exciting applications for these types of complexes. You can imagine they're used a lot in cosmetics, viscosity modifiers. They're also used in underwater adhesives. But really, my group is just interested in the very fundamental structure property relationships of these materials. So today, I will teach you about the phases and the molecular descriptions of polyelectrolyte complexes. Then we will go into our work on the glass transition and the dynamic mechanical behavior of these complexes. And then if we have time, I'll show you some unpublished work on doing some phase mapping for these complexes, kind of in the spirit of the Equiphase conference from last year. So I showed you a video of what it looks like when two oppositely charged polymers come together, but here's more of a chemical schematic where we have a polycation and a polyanion, and then they will associate together to form a complex. Electrostatic interactions really do help drive complexation, but it's entropy that is the major contributor. And this is because when the two polymers come together, these small counter ions are released into the external solution, and there's a huge entropic gain associated with that. Not only that, there's also a release of those hydrating water molecules. So the water molecules that were hydrating the polymer also get released. Some of them get released out into the external solution, further increasing the entropy. So overall, complexation is entropically driven, but the complexation itself can have an enthalpic contribution. It's usually a very weak contribution compared to the entropic gain. Now, once the complex is made, we need to think about the molecular structure. So please look at this cartoon on the left. This is going to teach you some vocabulary that you'll hear in the rest of the presentation. So when these polymer repeat units of opposite charge come together and associate, we call that an intrinsic ion pair, kind of like an internal ion pair. And then the opposite of that is a charge group on the polyelectrolyte that's associated with a small counter ion, so maybe like a sodium or a chloride. So your complex is actually going to exist, is going to consist of a mixture of these intrinsic ion pairs that act as crosslinks, and then these extrinsic ion pairs. And in the literature, people also call these extrinsic ion pairs doped sites because they're doped or compensated by a small counter ion. So we can go into the lab and control the ratio of intrinsic and extrinsic ion pairs by changing the salt concentration. We can use salt to screen charge and break up intrinsic ion pairs as the salt is competing for ion pairing. We can also use pH to control the number of intrinsic ion pair crosslinks. Some of these complexes or some of these polyelectrolytes are pH responsive. So of course, pH can have a major role. So our general theme in our group is that changing the number or the concentration of intrinsic ion pairing is going to adjust all of the physical properties that you'll see macroscopically. So to understand that, it requires us to form a way to count the intrinsic ion pairs and the extrinsic ion pairs, and then correlate that count to physical properties like the glass transition or the dynamic mechanical relaxation. So now I'm going to introduce you to some of the phases that you might see when you mix these two oppositely charged polymers. This is an experimental phase diagram of polyacrylic acid and polyalamine. The y-axis is salt concentration, and the x-axis is the fraction of polyacrylic acid. When you have very asymmetric mixtures, you'll get a clear solution. So the two polymers are in solution, but they're not associating enough to form an isolatable complex. In this region, where you're closer to about 50-50 by repeat unit or equimolar charge compensation, and you have a higher salt concentration, you can have what looks like a liquid-like coacervate. So this is a liquid-liquid phase separation, where the supernatant represents the solution, and then the bottom is the liquid coacervate, and it tends to have like a thick gel-like or honey-like consistency. And of course, if you add enough salt, you move upwards in the phase diagram. If you add enough salt, you can screen the interactions completely and come back to the solution. The last phase is the one that we work with the most in my group. It's the solid-like precipitate. It tends to appear in conditions of very low salt concentration. The complex can be feathery, very disorganized and ugly looking, and it's solid-like, and you can isolate it by centrifuging, and then we can dry it down and grind it into a powder for further characterization. So these are the challenges that I think about with regard to the future of polyelectrolyte complexes. I'm really interested in understanding this phase boundary between the solid-like precipitate and the liquid-like coacervate. Is there a thermodynamic origin to that, or is it just a question of equilibrium versus being kinetically trapped? Then the next thing I think about is the precipitate. It's very poorly characterized, it's disorganized, it's not easy to work with. And so it's also very path dependent, which gives you a clue that it's probably kinetically trapped as well. But we've developed ways and protocols to eliminate the path dependency as much as we can to characterize the precipitate, which is what you'll see today. Also, the chain dynamics of the polymer within the coacervate and the precipitate, it's very challenging to characterize. What is the diffusion of a polyelectrolyte chain when it has so many associations in that complex? And then what is equilibrium from one lab to the next? These complexes seem to be, they do have some path dependent characterizations. So what I publish could be different. My pathway could be different from another lab's pathway, and we may get different results. So those are things that we should all consider. So I want to count the intrinsic ion pairs and relate them to physical properties. And so experimentally, we do this by a combination of methods. We can use NMR and neutron activation analysis to analyze the ratio of the polycation to polyanion, because when we mix the polyelectrolytes, what we put in is not always what we get out, because one of our purifying steps is dialysis, where the extra unassociated polyelectrolytes can diffuse out. So we need to know of that complex we made, what's actually in it. We also use FTIR. If ionization is a concern, we can quantify the ionization of individual polyelectrolytes. We want to know the salt content in the polyelectrolyte complexes, because there can be salt partitioning in the solid or liquid phases. So there's a variety of methods we can use here. And then taking all of that together, that's going to yield the number of intrinsic versus extrinsic ion pairs. We're also interested in the water content. So sometimes we will dry out the complex and then purposefully add water back, so we know what water is doing to the glass transition and dynamics of the complex. And to give you an experimental point of view, this is how we prepare and characterize the complexes. So we'll mix the two complexes together, and then we'll do some dialysis. This helps equilibrate them and eliminate some of that path-dependent behavior that happened in the mixing process. Any unassociated polyelectrolyte will diffuse out of the dialysis bag. And so we can really isolate the complex. Then we can further isolate it with centrifuging. We air dry it, and then we can obtain a powder. The powder, we can do DSC to get the glass transition. We could also process the powder and do some compression molding for dynamic mechanical analysis. So the first system we're going to investigate is called PDADMA PSS. So these are two strong polyelectrolytes that are not responsive to pH. So I don't need to care about pH here. And these two polyelectrolytes are going to be mixed together in the slide I showed you. And we're just going to do some first characterization on them. So we isolated a solid precipitate, and we want to quantify the doping level or the fraction of extrinsic ion pairs. There's two doping levels, actually, one for each polyelectrolyte. So the polycation may be doped to a different degree from the polyanion. And so we can measure this and quantify it using neutron activation analysis. And this is the equation for how we do that. We have to make certain assumptions to move forward with the calculation. So we have to assume there's no co-ions. What that means is that any ion we detect, we assume that it is associated with an extrinsic ion pair. And then we also have to assume these two polymers are fully ionized. And so from that, we can get the mole fraction of PDADMA and PSS in the complex, and then the doping levels. So here what we observe is, regardless of the salt concentration at which I prepared the complex, I always have an excess of PDADMA, the polycation. And we've seen this for years. And there's reasons for this. PDADMA is a little more hydrophilic. It has a different linear charge density. All of these can come together to make a slightly asymmetric complex. Then we have the doping levels that we can measure. So as we increase the salt concentration of assembly, the doping level increases as well. So this is showing the effects of screening. The salt is breaking up intrinsic ion pairs up to a point. See, at 1 molar, we could say about 30% of the PDADMA is unpaired, or 30% of the PDADMA is paired with a chloride ion instead of a polyanion. So that's as an example. So with all of that data, we can estimate the number or the concentration of these intrinsic ion pair crosslinks in the complex. So we have to assume one of the polymers is kind of limiting and the other one is in excess. And this box over here is showing you how we can do that calculation. But essentially, we can estimate the concentration of the intrinsic ion pairs, or IP, as our concentration of the limiting polyanion times 1 minus the doping level. And what we were proposing at the beginning of the presentation was that this concentration of intrinsic ion pairs is going to really play a role in the bulk macroscopic properties. So I wanted to show you how we measure that, but now let's go measure some properties. Okay, so the first question is, how does glass transition vary with the number of intrinsic ion pairs? So we're still working with the same complex, and we know from work you're going to see that the number or concentration of intrinsic ion pairs varies with ionic strength, and then in other systems, it can vary with pH if you have a pH responsive polyelectrolyte. We are also going to see that the glass transition temperature varies with ionic strength. You'll see that here, and then in a few slides with a different system, you'll see that it varies with pH. And one of the curious things is that a glass transition in these complexes only appears if you add water. So water is going to plasticize this. So this is very important. So here is a modulated DSC thermogram of a dry PDADMA PSS complex. We have to do modulated DSC because the glass transition is very weak, and this method is very good for kind of amplifying the signal. If you were going to see a glass transition, it would show up in this red non-reversing curve, which contains all the heat capacity information. But you see nothing. So dry polyelectrolyte complex, no glass transition. When you handle it, it's really brittle. But if we add some water, 28% water, look in this red non-reversing curve, we have the appearance of a glass transition. And what we've seen is that the glass transition will move around depending on how much water is in there, also how much intrinsic ion pairing you have. So what we did was we measured the glass transition for these p-DADMA, PSS, PECs that have been assembled in different salt concentrations. So they're going to have different extensive ion pairing. We used the method before to quantify the number of intrinsic ion pairs. We also added varying amounts of water to move that glass transition around. And we discovered that the glass transition temperatures all collapse onto a single curve when we plot it against this ratio of water to intrinsic ion pairing. So this gives a first clue that the glass transition is mediated by some kind of mechanism of water at the intrinsic ion pair. Okay. Now, what's even more curious, if we take that same data and plot it just a different way, we retrieve a linear relationship, no adjustable parameters, but it's linear. So if we take the natural log of water per intrinsic ion pair versus 1/Tg, it's linear. And the slope gives you an energy of 10.8 kilojoules per mole, which is similar to Van 't Hoff enthalpy for a hydrogen mud. So this is another clue that there's some sort of interaction of water happening at the intrinsic ion pair to allow the polyelectrolyte chains to slide past one another and go through this glass transition and more macroscopic relaxation. Okay, so we know that that relationship holds true for one system at all these different salt concentrations. But what about another system? This is a different system that is very sensitive to pH. So we have polyalamine and polyacrylic acid, and they have the corresponding pKa's here. So we can make complexes with them at varying pH, and we can change the water content and measure the Tg just as before. And here's the result. So this says TTR, like a thermal transition, but it's really a TG. So this is the glass transition versus the water to intrinsic ion pairing ratio for all the different pH values of assembly. Again, they collapse onto a single curve with no adjustable parameters. So it's following the same relationship as this different system. And these are the two systems that we plot in the linear form I showed you. So these two different systems, p-DADMA, PSS, the strong polyelectrolytes, and pH, PA, the weak polyelectrolytes, both follow the same linearization. And you can see with just your eyes, they have about the same slope. They have different y-intercepts though, but they both have about the same slope, which gives you about the same energy. So this is pointing to the idea that maybe the way polyelectrolytes relax and through the glass transition in polyelectrolyte complexes, maybe it's a more general phenomena regardless of the polyelectrolytes you choose. Maybe it has to do with somehow that intrinsic ion pair has to be released momentarily with water mediating that release so that the polyelectrolytes can slide against one another. So we've been collaborating with Maria and Peter for over a decade now on trying to understand how these polyelectrolytes interact with each other and how water mediates that interaction through molecular dynamics simulation. So I just want to point you to a series of papers that their work is featured. And generally, their findings support the idea that water plasticizes the complex and it perhaps increases the free volume, which may allow for more opportunities for the glass transition to occur. Water lubricates and weakens the intrinsic ion pair. And the intrinsic ion pairs are acting as temporary cross links. So if you can go through a glass transition if you can increase the frequency at which these intrinsic ion pairs temporarily dissociate, but you can also encourage the glass transition by changing the number of intrinsic ion pairs. And this can be done with salt and pH. So something that I've been thinking about for years is why are there different y-intercepts? And there's so many possible reasons. So when we do this calculation for the water, we're taking water as the total amount of water added into the complex. But we have to be honest with ourselves. When water goes into the complex, it can exist in multiple different microenvironments. Some of it can be bound at the intrinsic ion pair, some of it can be bound at the extrinsic ion pair, some of it could be freely existing. So we don't really know how much water is at the intrinsic ion pair. And that may be a reason that this y-intercept, these systems have different y-intercepts, because this would move it up and down. We also have another explanation at the end of this presentation for why there's different y-intercepts, just for your consideration. So to partly explore this idea of quantifying water at the intrinsic ion pair, we turned to a really interesting paper from Joe Schlenoff's group. So what he did was he used FTIR spectroscopy on polyelectrolyte multilayers, which are like complexes, but they're thin films. And what he did was he tried to separate out how much water was at the intrinsic ion pair and how much was at the extrinsic ion pair. And really the main point is that he measured this ratio of water against one of the polyelectrolytes. So it's almost like a swelling ratio. And he changed the salt concentration. And at really high salt concentrations, you get into a regime where you're linearly doping the film. And he fit a line to this linear behavior at the high salt concentration, where the slope of this linear fit is a hydration coefficient, and I, which is the y-intercept, and I is what we're after. I will be the number of water molecules at the intrinsic ion pair. So the method he used is a little challenging overall. So we chose to try to develop a parallel method using quartz crystal microbalance with dissipation monitoring. And it's just a method that can measure the swelling of the film. And we can plot the data in the same form that he had. And we also get a linear regime where these polyelectrolyte multilayers assembled in different salts and exposed, and then later exposed to different salts, they have a linear doping regime as well. So we fit the slope and the y-intercept. And what we find is that we're getting 15 to 23 water molecules per intrinsic ion pair, which sounds really high. I mean, if you think about an intrinsic ion pair and then, something like 20 water molecules around it, it sounds a little crazy, but at the same time, other methods like NMR have seen 20 to 25. The FTIR method I mentioned showed 7 or 6.9 water molecules here. So what we think is, depending on the method you use, you're probably accessing water in the first hydration shell, and maybe with our methods, outer hydration shells that are less they're correlated with the intrinsic ion pair, but less so than that first hydration shell. So that is one of these methods that we're considering to address the y-intercept. But if you stay tuned, I'll give you another thing to think about for that y-intercept. So let me move forward to dynamic mechanical relaxation of complexes. So we next, I want to go through this idea of the polyelectrolyte relaxing in the complex. So if you go through a glass transition, there's a relaxation. You can also see a relaxation using dynamic mechanical analysis, which is a method that holds your polyelectrolyte complex film and applies a sinusoidal tension, and you can look at the in-phase and out-of-phase responses. Here's a plot of a pH-PAA polyelectrolyte complex prepared at, I think this one is at pH 7, and we had gone through a series of temperatures and measured the frequency-dependent storage modulus at a certain relative humidity. So with that relative humidity, you know how much water is in there. And with this data, we performed time temperature superpositioning. So here's an example of storage modulus taken at all these different temperatures. And then we can horizontally shift them using superpositioning, where AT is called a shift factor. And that shift factor AT follows an Arrhenius law. Now, what we do on the next slide is we measure the storage and loss modulus, but we're just showing you the storage modulus here at different humidities. So now we have all these time temperature shifted curves, but taken at different relative humidities, okay? Because water is going to change the relaxation. We perform a horizontal shift, and we have to add in a second shift factor depending on water. And with that shift, you can see there's reasonable overlay of the data. So now we've done time, temperature, water superpositioning to describe the mechanical behavior of the complexes. So we can combine those in a combined shift factor, where this is your Arrhenius shift factor that includes the temperature dependence. But then we have this kind of log linear relationship with the water content, where here we're taking the weight percentage of water in the complex, which we've measured separately. So it's really interesting because we're not the first to see that log linear behavior for the relaxation, but we were able to confirm that. Now, the relaxation time can be taken as where the tan delta, which I'm not showing here, is 1. And we're getting really long relaxation times. These complexes are very brittle and very tightly bonded. So they need long times to see any relaxation. Now, what we were able to do was also take a relaxation time as the crossover of the E prime and E double prime data. And that gives, from that frequency, we can get a relaxation time. We know the amount of water at each of these relative humidities inside the complex, which we can convert to a volume fraction of water. And we plotted that the natural log of the complex's relaxation time varies linearly with 1 over the volume fraction of water in the complex. And so no adjustable parameters, but we see this very robust linear relationship. In this case, for all of these complexes, the water, we know from other DSC experiments, the water is tightly bound in the complex. It's not free water. So in this case, we know all of our water is interacting with charge groups. So this seems to hold very well for that. This was done only at a single pH though, pH 7. Will this hold up if I change pH? So here's an example where we also explored pH 4.5, pH 7. We did time, temperature, water superpositioning to get these nice curves. We see the crossover frequency is increasing as pH decreases. That relates to a decrease in the relaxation time. Ionization of the polyacrylic acid is, of course, changing, but we can characterize that with FTIR to complete our intrinsic ion pair calculation. Now, if we try to plot the natural log of the relaxation time with 1 over the volume fraction of water for within a single pH, yeah, it's linear, but they don't collapse onto the same curve. So it means that within that pH, the relationship holds, but it's not general to the whole system. However, if we take the same data but plot it against the ratio of intrinsic ion pairs to water, then it collapses into a single curve with a very good linear fit. And again, no adjustable parameters. So this result indicates that the natural log of the relaxation time of a polyelectrolyte complex is related to the ratio of intrinsic ion pairs in water. So we're getting back to almost the same type of relationship we're seeing for the glass transition. And this, again, is valid when the water is bound. If you have free water, this complicates the calculation because you don't know how much water is really interacting with the polyelectrolytes. So this slide summarizes our findings over the last few years with these relationships. But now I want to move into some of the ongoing things that we've been discussing and working on in my group. So I've presented this relationship to you, and it seems empirical or phenomenological at first, and we've been really struggling to come up with a physical a relationship from it based on physical principles. And you'll see one of our first ideas about it in the next few slides. So we've been plotting, we can plot it both of these ways. And it's kind of hard to say which way to plot it because it says, this is saying that if I input this TG, then then the output is this ratio, or if I input this water and intrinsic ion ratio, the TG is the output. So it's kind of hard to, without having a physical meaning behind it, to know the best way to represent it. So this is not yet published, but it is in review at Langmuir in a perspective we're writing. So I wanted to present this to you briefly. So consider an intrinsic ion pair with, let's say, 4 water molecules there. I just picked 4 arbitrarily. And we're going to add 1 water molecule. And that water molecule can now enter the hydration shell around that intrinsic ion pair. And the idea is that that additional water molecule may be enough to loosen or weaken the interaction between the oppositely charged polymers. The opposite charges remain correlated, but it may be just enough to weaken the electrostatic interaction, which we represent here. Now, imagine that there's some equilibrium that occurs between these 2 states. So I can write an equilibrium equation here, where X represents the change in concentration due to the conversion of these intrinsic ion pairs into the weakened state. And that equation came from assuming initially I have this concentration of intrinsic ion pairs, some concentration of water. There's some change in them leading to these final concentrations. And so that led to this equilibrium relationship I'm representing. Okay. Now, we propose that there exists some critical fraction of sufficiently solvent separated or extra hydrated intrinsic ion pairs, Y, for which a bulk scale relaxation is permitted, such as a glass transition or that relaxation time we saw in dynamic mechanical analysis. So here is a picture where I'm trying to draw that, where these are still correlated, but they're slightly separated because there's been additional water molecules input into them. So we may say Y is 3/5, and maybe that's enough to allow some relaxation that we might be able to observe. So with that parameter, Y, we introduce that into our equilibrium equation here. Okay. And then we make one assumption. We assume that Y times the concentration of intrinsic ion pairs is much less than the concentration of water to get this new relationship. And now we're going to bring in a Van Hoff type relationship, where we say the natural log of our equilibrium constant is related to an enthalpy and an entropy here. Okay. So by bringing that in, we can now say the natural log of our intrinsic ion pair to water ratio by concentration or by number, because they're all in the same volume, will scale with 1/t. And if y here is that critical fraction required to undergo the TG, then this T becomes TG. The slope would have that enthalpy, and then y-intercept would include an entropic term and then another term that relates the critical fraction of polyelectrolyte, or critical fraction of a weakened polyelectrolyte to go through the glass transition. And so by that interpretation, if I come here, we may plot the data slightly differently. This interpretation is saying we could plot the natural log of intrinsic ion pair to water against -1/Tg. So we could do that. But it's equivalent to how we were plotting it before. Now, you look at these two different systems, they have different y-intercepts. Now we can discuss perhaps the different y-intercepts are due to either and differences in entropy and this y value in the systems. We can also replot our old results. So here's an example where we replot our old results as the natural log of the intrinsic ion pair to water ratio and -1/Tg. It looks the same, and it'll have the same slope and the same sort of interpretation. I think I've been talking for about 40 minutes, so I just want to quickly touch upon the last thing we're doing, and I'll sum up because I was told this presentation should be 40 minutes long. So the last thing that's ongoing is we're trying to understand these phase boundaries. So I just want to show you these complexes can have UCSTs or LCSTs or both. And so we're trying to understand what drives that, whether it's entropic interactions with a Flory-Huggins interaction constant or dielectrics. And so in our unpublished work, we're now making phase maps of solutions, coacervates, precipitates, and how that relates. And so here's a picture of a liquid-like coacervate. It makes these beautiful droplets, these messy precipitates. And we can also induce these UCSTs in the system. So hopefully next time I could tell you more about that after it's online. Okay, and so there's a couple videos of these complexes undergoing UCSTs. As you heat them up, the optical field becomes clear. And when you cool it down, these complexes can reappear. So it's really fascinating. Okay, so in conclusion, we are learning that the glass transition and relaxation of complexes is facilitated by water's ability probably to weaken or lubricate the intrinsic ion pair. We think there's a critical fraction of weakened intrinsic ion pairs required to go through that relaxation. And then our future work, there's so much future work, but here's a few things that we're thinking about: molecular weight effects, divalent ions, that's really interesting, anion effects, and then those boundaries. So with that, I'm going to stop, and I really want to thank Chika and Suvesh, my current PhD students who've done a lot of the work that you've just seen. So thank you so much, and I look forward to your questions.